The third part of the tutorial deals with channel characterization, and is interestingly pointed out by reference 27, in the case of cooperative networks, the network actually becomes part of the channel. We will henceforth deal with three different cases. We will look at the channel for regenerative relaying, meaning from a base station to a mobile station, and then the mobile station regenerates a signal and retransmits to the next relay or to the destination. The second case will be the channel for transparent relaying, which is a cascaded channel where the base station broadcasts a signal, it is being picked up by the relay, it is amplified, and then relayed to the next relay or to the destination. We will also look into the distributed MIMO channel behavior. We will ask the question, what are the characteristics of a channel where you may have several distributed transmit and several distributed receive antennas? Coming to the regenerative relaying channel, I would like to present you a few trends where I've shown 4 different cases here. The first case is the narrowband non-cooperative case, which is the baseline case. Then on the right hand side we have the wideband non-cooperative, and below here we have the cooperative cases. So on the left we got the narrowband cooperative, and on the right we got the wideband cooperative case. What I'm depicting here is a field strength versus distance, and as we know, the power loss versus distance is composed of 3 multiplicative effects. The first one being path loss, second being the shadowing, and the third one being the small scale fading, which is the one which is measured in the end right here. So if we have a free space case, we have a loss of minus 20 dB per decade, but because we got some clutter, and that clutter causes some shadowing, and that shadowing mean is absorbed in the path loss, we get a slope which is steeper than 20 dB per decade, and we therefore get a slope which might be minus n multiplied by 10 dB per decade, where n may vary between 2 and 6. The shadowing process also depends on distance, depends on cell size, it depends on the environment, where typical values range between 2 and 16 dB. And then you got the small scale fading, which is seen here, and that is the actual fading which is measured by my terminal. On the right hand side we got the wideband case, where you see that we got a reduced fading. The reason being is because our wideband transceiver is able to pick up more diversity, and therefore you would have less fading. Just for those who really deal with channel models, another effect with wideband is that the average path loss is pushed up a little bit because my wideband transceiver is able to receive more power, and therefore that curve here, the path loss curve, is shifted slightly to lower values. We have then the narrowband cooperative case, and the first thing we observe if we compare with the narrowband non-cooperative cases, that the aggregate path loss is less, so the steepness of that path loss might be well below minus 20 dB per decade, and it depends on the relays, on the relay positioning, on the way the power allocation is done. But generally you will observe that the aggregate path loss using relays is less than the path loss you experience if you had a direct link. We will also see later that the fades are deeper and that the fades are more frequent. That means they happen more frequently than in the case of the non-cooperative transceiver, so we have fades which just happen more often. We also observe that the shadowing has a slightly reduced variance. The reason being is because the cooperative terminal provides ideally a shadow uncorrelated version of the signal and therefore counteracts shadowing very well. That of course requires that the relay terminal is out of the shadow coherence distance of my direct link. Now as for the wideband cooperative case, we do have the same tendencies, with the only difference that my fading is reduced further, again because my wideband transceiver is capable of picking up diversity in the frequency domain. I have listed a few general channel parameters which had been compiled from reference 28 till 40. For each of them, I will give figures for the traditional links, which is from a high base station or access point down to a lower embedded mobile terminal, and then for the cooperative links, where you have terminals, cooperative terminals embedded in clutter, and they communicate directly with each other. Now I will just skip briefly over these slides. You're welcome to pause the presentation and copy these values, which are indicative values because measurements do not exist in that large quantity as of yet. So what I've listed here is the path loss. That is an interesting value. So we got the path loss coefficients, the shadowing variance, and the shadowing coherence distance to judge whether my cooperative terminal is out of the coherence distance. I also looked at the first multipath component fading statistics, at the power delay profile, and at the root mean square delay spread, the RMS delay spread, which, by the way, you can calculate by taking the largest dimension of your environment, for instance, the size of your room, and you divide it by the speed of light. That gives you quite good value for the tau RMS. Also, if you're interested in specific channel models which exist already, for instance, for the path loss and channel models, I've given a few models here, and these are useful for the traditional link from a base station or an access point down to a mobile station. Also, an interesting one are the indoors and wireless LAN models, which have been used extensively. That can be used also for the traditional link or also for the cooperative link. And finally, you got models which are more suitable for cooperative links, which stem from the Zigbee and ultra-wideband community, which can be found right here. Let's move on to the temporal characteristics of the regenerative relaying channel, and what we assume here very rigorously is a SISO channel, a narrowband channel, and a 2D isotropic scattering channel, where two mobile terminals which may move with a different speed are embedded into that scatter. The models developed here come from references 42 till 45. Particularly, we look at the autocorrelation function, which for a traditional link is a simple Bessel function, and in this case is given as a product of two Bessel functions, which is exactly taking care of the fact that we got one mobile, my transmitter moving, and my receiver moving, where these expressions are almost the same except for factor A, which caters for the Doppler frequency offset. The Doppler spectrum has also been calculated by the authors and is a slightly more complicated version than that U-shape which we are familiar with. The level crossing rates and the average phase durations have also been derived, where the level crossing rate is defined as the expected number of times per second the channel envelope crosses a level gamma in a positive direction, and the expression is given here, where F1 is the Doppler frequency, ρ is the normalized level, and A is the frequency shift which has been given before. The average phase duration is the average duration of time the envelope spins below a certain level gamma, and has also been derived by the authors given by that expression here. Now these two expressions are very interesting if you look at an opportunistic relaying system where you would like to schedule data according to channel availability, and therefore that expression here, LCR, the level crossing rate, tells you how often my scheduler will have a chance to transmit something, and the average phase duration will tell us if it is able to transmit something, how long on average will it be able to transmit a certain data packet. Now if we look at the temporal characteristics, where I plot here the autocorrelation function versus the time lag, I plot you the traditional base station to mobile terminal Bessel function, where we assume that the mobile terminal moves at 1 meter per second, and also the green dotted line is the regenerative relaying channel, where both mobile terminals move at a speed of 1 meter per second. And as you can see, that function here goes down to zero much faster. Therefore, my channel, my regenerative relaying channel, decorrelates faster than my traditional base station to mobile terminal channel. Now that has a few implications for the transceiver design. It is very good for the code design because as such my coder is much better in shape to pick up the time diversity. Alternatively, we get away with the interleavers of much lower depth, but it is bad for channel estimation purposes because my channel changes very rapidly. Therefore, we trade one against the other, and whilst you may get away with a weaker coder, you may need to switch to differential modulation. For the level crossing rates, as you can see, I plotted here the level crossing rate 1 per second versus the crossing level, and here again is the traditional base station to mobile terminal link, where the mobile terminals are again assumed to move at 1 meter per second, and we got the regenerative relaying link, which shows a much higher level crossing, which means that from a scheduling point of view, we have a much higher fairness because we are able to schedule or to serve many more people in the same time period as if we just used the base station to mobile terminal link. But on the other hand, we need much more frequent channel updates, which is of course a signaling burden. The model which I presented stemmed from Aki's results and had been then extended by Patel and Stuber, but more general models are available today, and for instance a more general fading distribution has been considered in 46 and 48 because the model I presented to you just assumed Rayleigh fading. Also, as I said before, we assumed isotropic 2D scatterers. Now that had been extended in 49 to non-isotropic scatterers. Also, the extension from 2D to 3D has been performed in 50, and the extension from SISO to MIMO to multiple input, multiple output channels has been performed in 51 till 55. A few measurements have also occurred in recent years and can be found in 56 and 57. We finish now with the regenerative relaying and move on to the transparent relaying channel. And again, I would like to present you a few tendencies. And we got our baseline case here, narrowband and non-cooperative and wideband non-cooperative, which remain unchanged. Contrary to that, the narrowband cooperative case changes now, and as we can see, not only do we have more frequent fades, but we also have fades which are much deeper in amplitude, and I will explain you later why this happens. So we bear in mind a transparent relaying channel will have more or less the same tendency as a regenerative one, with the only exception that the fades are significantly deeper. If we go to the wideband cooperative case, we see that the fades are reduced and otherwise the tendencies remain the same, which means we have less aggregate path loss and we have a reduced shadowing variance. To exemplify that, let us concentrate on a very simple two-hop transparent relaying channel which has been well exposed in references 44 till 45, and what we assume here is an AF, an amplifying forward transparent relaying protocol where base station broadcasts a signal. It is being received and amplified by a relay mobile terminal and transmitted to a target mobile terminal. We see what the relay mobile terminal receives from the base station, which is exactly that expression here. Let me highlight that. That is this expression here, which is being picked up by my relay terminal, where S is the transmitted signal, H1 is the narrowband channel, fading channel from the base station to the relay mobile terminal, and N1 is the wide Gaussian noise which is being picked up by the relay terminal. That is then amplified in the relay terminal using an amplification factor A, and transmitted through a wireless channel H2 until it reaches my receiver, my target receiver, within which an additive white Gaussian noise is added N2. So to summarize, we got A being the amplification factor, H1 is a channel between base station and relay mobile terminal, and H2 between relay mobile terminal and target mobile terminal. Both channels, wireless channels, are modeled as zero-mean complex Gaussian channels with the respective powers sigma 1 square and sigma 2 square. N1, 2 are the respective additive white Gaussian noise terms with an equal power n. P1 is the transmission power at the base station, and P2 is the transmission power at the relay mobile terminal. Now we have a few choices to get that amplification done. We will stick to two. One is the fixed gain relay proposed in 58, where you would adopt the amplification factor according to some constraints, and you end up with having here just the average power of the first channel. Therefore, we only need statistical knowledge of the first hop channel and nothing else, so that can be fed in at the beginning of my transmission and then be used as a constant relay factor. In the case of variable gains, which has been proposed and analyzed in 59, we replace the average power by the instantaneous channel realization H1 square, and that of course requires at the relay terminal an instantaneous knowledge of the first hop channel, and therefore that has to be provided and fed to the relay channel. Other application-dependent factors have been proposed, but we will not consider them in this presentation. Now I'm showing you the PDFs which have been developed for the case where you have a fixed gain and for the case where you have a variable gain. In particular, for the fixed gain, we assume without loss of generality that A equates to 1, and we get a PDF which is quite curious and deviates from the negative exponential which we are familiar with in the case of the relay channel. The reason being is because of instead of having a simple channel realization, we have the product of two Gaussian channels here, and therefore leading to a PDF which is given here. We observe that actually that PDF is symmetric in the product of the channel power of both channels and is given by means of a zeroth order modified Bessel function of the second kind. In the case of variable gain, things change considerably, and I remind you again of the statement I'd given at the beginning of that section and saying that the relaying network becomes part of the channel, and that is exactly what is happening here, because using a more sophisticated way of accomplishing the relay amplification, you get a PDF which is very complicated and given in that term here. If we look at the tendencies, we will look first at the fixed gain two-hop relaying behavior. In particular, I plotted three curves here. I plotted the well-known single-hop relay, which is in a bit of an unusual shape here, but this is due to the scaling of that amplitude. In addition, I depicted the fixed gain two-hop relay, where you have equal power in both links, and that power is given here. It is 0.5 and 0.5. Then you have the third case, you have fixed gain two-hop relay. In this case, the power is imbalanced. My first channel is much stronger than my second one, the first channel being 0.9 and my second one being 0.1. Now we observe something quite interesting, and that is that there's a higher probability that amplitudes of lower values are realized. That means whilst we had the maximum for the relay channel here in terms of PDF, so a large likelihood that my channel will be realized is here, that is now shifted to lower values, causing exactly the deep fades which I referred to before. So therefore, we bear in mind the transparent relaying will cause deeper fades, which is given in these PDFs here. Now here I compare the variable gain with a fixed gain. Again, I gave as a reference a single hop relay case, and then we look at the fixed gain, two hop relay, and the variable gain one, and we observe that the variable gain manages to push back some of these amplitudes to higher values, so that is better news, but it is not as good as you had just a single hop relay. But please bear in mind that there are more underlying effects than the channel statistics itself. You got reduced shadowing, and you also have a reduced aggregate path loss, which leads on the long run to a better performance generally for the relay case. As for the temporal characteristics, in the case of the regenerative, in case of the transparent relaying channel, we do have now three Bessel functions here, which stems from the fact that my relay terminal moves. He received the signal at the frequency with wavelength lambda 1, and he moves with the speed v1, therefore causing a Doppler f1 here, which is reflected in this coefficient here. Then he retransmits that signal transparently. He still moves at the speed v1, but of course must use a different frequency lambda 2, from which stems that factor here. Finally, the signal is received by my target terminal, which moves at speed v2 and uses the same carrier frequency as we had used before, and this leads to that coefficient here. So we do have now an autocorrelation function which is composed of a product of three zeroth order Bessel functions of the first kind, and that leads to quite interesting behavior, as we will see on the subsequent slide. Patel and Stuber also managed to derive the temporal autocorrelation function in the case of a variable gain, which is not very straightforward to do. They found an approximation, particularly for larger time lags, and that expression is given right here, where 2f1 is a Gauss hypergeometric function. If we plot this function, again, I plotted as a reference my traditional base station to mobile terminal link, where the mobile terminal moves at 1 meter per second, and we have a fixed gain mobile to mobile terminal link here, which is given right here, and the variable gain, where I remind you it does not hold for low values of the time lag, so that expression is truncated. As we can observe, again, the relay channel decorrelates faster, which is good for the co-design, as I had alluded for before, but is not as good for channel estimation purposes. Let's move on now to the distributed MIMO behavior. And what we are interested in is a scenario like that one here. We got an information source. It is transmitting data to a channel encoder that is passed to distributed antenna elements here, which form a fractional spacetime code word. So that one here picks up part of this spacetime code word, that one here and that one here. They transmit it in a distributed fashion through a channel which is given here to a receiver, which also might be distributed, having R receive antennas. That is then fed into a space-time decoder, goes then to the channel decoder, and finally to information sink. Now, having T distributed transmit antennas and R distributed receive antennas, we will have R multiplied by T channels in general. They are given here as H11, etc., until HRT, and squeezed, as we know, into a channel matrix given right here. Now that channel matrix is a neat tool, but does not really visualize well what is happening in my MIMO channel, and for that reason, according to 60, we use a unitary transformation to perform a Fourier transform, a spatial Fourier transform on that channel H, to obtain H omega, which gives us information over the spatial domain. So we end up with a channel H omega, which is given here, and which tells us which of the angular domains have been resolved. For example, we have T distributed transmit and R distributed receive antennas here. We have a few clutter in space here, and they communicate. As you can see, these clusters here are being resolved, and this one here on the receiving side, which would be reflected in my angular matrix H omega. If we look at that matrix H omega, we can derive a few conclusive insights. First of all, the rank of that matrix. The rank, which gives us the degree of freedom, is the minimum number of non-zero rows and non-zero columns in H omega. It would depend on the amount of clutter in the channel and the antenna separation, meaning if you have a lot of clutter, you are likely to have a large rank, so a high degree of freedom, and it determines eventually the data multiplexing capabilities of the channel, so it tells you what data rate this channel can support. Then we have the diversity gain, which is dictated by the number of non-zero entries in H omega. It depends on the connectivity of the channel, meaning how many connections are between each transmit and receive antenna, and it determines the reliability of the channel. And finally, we got the power gain, which is determined by the conditioning number. If you eigenresolve that channel, you can obtain the largest and the smallest eigenvalue. You form the ratio between both, and you obtain the conditioning number. If that conditioning number is very large, that means we have a strong correlation in the channel. That means that beamforming is very, very useful. If, on the other hand, the conditioning number is small, close to 1, for example, then we do know that beamforming capabilities are not very useful. Now, let me exemplify you the degree of freedom and the diversity gain, and to this end, I choose an example of 3 transmit and 3 receive antennas, and we would have an angular matrix which has exactly 3 by 3 entries here. And let us assume that our first channel has non-zero entries here, here, and here. And as you can tell, the minimum number of non-zero rows and non-zero columns is 2. So therefore, my degree of freedom, my rank, or my data multiplexing capability is 2. As for the diversity gain, we said is the number of non-zero entries, and that one is 3. So therefore, the reliability is 3 of that channel. I remind you, the multiplexing 2, reliability 3. If, on the other hand, we would have the same number of rays which are going through the system, being resolved but in a different manner, we populate now the diagonal entries of that channel H omega, and we see that in this case we have 3 numbers of non-zero rows and non-zero columns, so therefore my data multiplexing capability is 3, whilst my diversity gain still remains 3, meaning that we can transmit more data through that channel here at the same reliability as up here. To summarize that, in a distributed topology, we are likely to have my relays submerged into rich clutter, which means in clear text from previous slides, my distributed MIMO will be full rank, so we have maximum degrees of freedom. It's good for data throughput. It will be fully connected. We have a good diversity gain, so we can trade very well one against the other. And it will be well conditioned, meaning we will have a little beamforming gain, so the range will still be quite limited in these type of systems. Now that concludes the section on channel modeling, and we will move on to physical layer design.